A digital signal is a signal that represents a sequence of discrete values. A logic signal is a digital signal with only two possible values, and describes an arbitrary bit stream. Other types of digital signals can represent three-valued logic or higher-valued logics. A digital signal is a physical quantity that is alternating between a discrete set of waveforms. Alternatively, a digital signal may be considered to be the sequence of codes represented by such a physical quantity. The physical quantity may be the alternating current or voltage of an electrical signal, the light intensity of an optical signal, the signal strength of a radio signal or acoustic signal, the magnetization of a magnetic storage media, etc. Digital signals are present in all digital electronics, notably computing equipment and data transmission. With digital signals, system noise, provided it is not too great, will not change the quantification, whereas with signals handled using analog processing, noise always degrades the operation to some degree. Definitions in different contexts. The term digital signal has related definitions in different contexts. In digital electronics, a digital signal is a pulse train, i.e., a sequence of fixed-width square-wave electrical pulses or light pulses, each occupying one of a discrete number of levels of amplitude. A special case is a logic signal or a binary signal, which varies between a low and a high signal level. In signal processing and digital signal processing, a digital signal is a representation of a physical signal that is sampled and quantified. A digital signal is an abstraction which is discrete in time and amplitude. The signal's value only exists at regular time intervals, since only the values of the corresponding physical signal at those sampled moments are significant for further digital processing. The digital signal is a sequence of codes drawn from a finite set of values. The digital signal may be stored, processed or transmitted physically as a pulse code modulation signal. In digital communications, a digital signal is a continuous time physical signal, alternating between a discrete number of waveforms, representing a bit stream message. The shape of the waveform depends on the transmission scheme, which may be either a line coding scheme, which produces a pulse-modulated signal, allowing baseband transmission, or a digital modulation scheme, allowing passband transmission over long wires or over a limited radio frequency band. Such a carrier-modulated sine wave is considered a digital signal in literature on digital communications and data transmission, but considered as a bit stream converted to an analog signal in electronics and computer networking. Logic signal. In computer architecture and other digital systems, a waveform that switches between two voltage levels representing the two states of a Boolean value is referred to as a digital signal or logic signal or binary signal when it is interpreted in terms of only two possible digits. The clock signal is a special digital signal that is used to synchronize many digital circuits. The image shown can be considered the waveform of a clock signal. Logic changes are triggered either by the rising edge or the falling edge. The given diagram is an example of the practical pulse, and therefore we have introduced two new terms that are rising edge, the transition from a low voltage to a high voltage; falling edge, the transition from a high voltage to a low one. Although in a highly simplified and idealized model of a digital circuit we may wish for these transitions to occur instantaneously, no real-world circuit is purely resistive, and therefore no circuit can instantly change voltage levels. This means that during a short, finite transition time, the output may not properly reflect the input, and will not correspond to either a logically high or low voltage. Logic voltage levels. The two states of a wire are usually represented by some measurement of an electrical property. Voltage is the most common, but current is used in some logic families. A threshold is designed for each logic family. When below that threshold, the wire is low. When above, high. Digital circuits establish a no man's area, or exclusion zone, that is wider than the tolerances of the components. The circuits avoid that area, in order to avoid indeterminate results. 5 VDDV equals 6V. It is usual to allow some tolerance in the voltage levels used. For example, 0 to 2 volts might represent logic 0, and 3 to 5 volts logic 1. A voltage of 2 to 3 volts would be invalid, and occur only in a fault condition or during a logic level transition. However, few logic circuits can detect such a condition, and most devices will interpret the signal simply as high or low in an undefined or device-specific manner. Some logic devices incorporate Schmitt trigger inputs whose behavior is much better defined in the threshold region, and have increased resilience to small variations in the input voltage. The levels represent the binary integers or logic levels of 0 and 1. Inactive high logic, low, represents binary 0 and high represents binary 1. Active low logic uses the reverse representation. Modulation. To create a digital signal, an analog signal must be modulated with a control signal to produce it. As we have already seen, the simplest modulation, a type of unipolar line coding, is simply to switch on and off a DC signal, so that high voltages are 1, and low voltages are 0. In digital radio schemes, one or more carrier waves are amplitude or frequency or phase modulated with a signal to produce a digital signal suitable for transmission. In asymmetric digital subscriber line over telephone wires, ADSL does not primarily use binary logic. The digital signals for individual carriers are modulated with different valued logics, depending on the Shannon capacity of the individual channel. Clocking. Often digital signals are sampled by a clock signal at regular intervals by passing the signal through an edge-sensitive flip-flop. When this is done, the input is measured at those points in time, and the signal from that time is passed through to the output, and the output is then held steady till the next clock. This process is the basis of synchronous logic, and the system is also used in digital signal processing. However, asynchronous logic also exists, which uses no single clock, and generally operates more quickly, and may use less power, but is significantly harder to design.